Okay, this video has the demonstration for an example of designing an FIR bandpass filter with a window. All right, so let's design a 9-tap bandpass filter. First thing I would do is find out what the cutoff frequencies are. FC1 is going to equal to 10 over 50 kilohertz, which is 1/5, and FC2 is equal to 20 over 50 kilohertz, which is equal to 2/5. All right, so then I can find omega C1, which is equal to 2 pi times FC1, so 2 pi over 5, and omega C2 is equal to 4 pi over 5. Same reason. All right, next I would calculate x. X is equal to 9 minus 1 over 4, over 2. 9 minus 1 over 2, which is equal to 4. And then what I know is that H bandpass filter of omega is going to equal to e to the minus j omega 4 for omega between omega C1 and omega C2, and it's also equal to e to the minus j omega 4 for minus omega C1 is greater than omega, and omega is greater than minus omega C2. And it's 0 everywhere else. So to figure out what H bandpass filter of N is, H bandpass filter of N, let's correct that up there, of N is equal to the inverse Fourier transform of this. It's equal to, and remember this is just a shifted version of my values. All right, I need to have a rectangular value and I need to shift it by 4 samples. Okay, so I'm going to take the inverse Fourier transform, which is the integral from minus omega C2 to minus omega C1 of e to the j omega n e to the minus j omega x d omega, and plus to that omega C1 to omega C2 of e to the minus j omega x e to the j omega n d omega. All right, which is going to result in the following. It's going to equal to 1 over 2 pi, 1 over j n to the minus x. All right, 1 over 2 pi multiplied by 1 over j n minus x, multiplied by e to the minus j omega 1 n minus x, minus e to the minus j omega 2. That's not a very good 2. J omega 2 n minus x. All right, plus e to the j omega 2 n minus x minus e to the minus j omega 1 n minus x. Now, this whole thing here looks a little bit familiar. All right, using Euler's formula, I can see that I'm going to get some sinusoids. So as a result, what I'm going to find is that I'm going to get equal to 1 over pi times n minus 4 sine of 4 pi over 5 times n minus 4 minus the sine of 2 pi over 5 times n minus 4. Now, this is a bit interesting because essentially what I've done is I have you can see, taken a set of filters, which would be familiar looking, and subtract them. And so that's actually quite interesting. That detail could be left up to a different point, but we know that we can actually do filter design the smart way. And the smart way is to, for a bandpass filter, is to take a low-pass filter and a high-pass filter and connect them together. And so as a result, I get something that looks like this. All right, so essentially what I would be doing is multiplying these things together, which is the same as putting a bandpass filter, or sorry, a high-pass filter in series with a low-pass filter. All right, so you could work out the details for this, but essentially this is really good to see that we get something that looks like this. Now, to bring this back to windowing, what I want to do is apply the Bartlett window. All right, apply the Bartlett window. And so the windowed version is equal to 1 over pi n minus 4 multiplied by, and then it's going to be this same exact value here, and I'll clean it out a bit. Let's grab these. It's going to look like this, except of course I can erase this particular thing. Okay, and then what I would do is take that and multiply it by 1 minus 2 to the n, or 2 times n minus 4, all divided by 8. Okay, so really everything that we have learned about filter design for FIR filters it applies here. I just am going to need to multiply by the windowing function. All right. Last little note before I conclude, just a quick reminder that H for a high-pass filter is equal to minus, and assuming that we're at n, is equal to minus 1 to the n of H low-pass filter of n. So just a reminder that usually we design our high-pass filter by designing a low-pass filter, but we need to keep this in mind. This is a little hint for doing some specific types of problems.